Hi, today we're going to be discussing the forecasting and data analysis behind forecasting of blood donations. And we're going to ask for a little bit of help from some vampire bats because as our teacher and mentor, Doc Larry, says, if we're not having fun, we're not doing it right. And we need to add a little bit of fun because of the perils of what we do. Everyone that confuses correlation with causation eventually ends up dead, and that's just a hazard of what we do. So we try to keep it a little bit lighthearted with some humor. Today what we're looking at is dynamics behind blood donation. So people donating blood for medical reasons to provide transfusions for other patients. And the dynamic in the graph below shows a cyclical dynamic and shows a difference between repeat donations and first-time donations. And the differences between that are obvious. Some people go in on a predictable time frame and donate blood, while others do it as part of another group activity or as other parts of blood drives. This graph shows the effects of 9/11 and how that event caused a spike in blood donations and a drastic change in how many people went in and donated blood for the first time. And we also found this data from the Ontario area showing the discrepancies between age and sex of who is donating, who are the highest percentage of donators for their age, class, and their gender. We look to vampire bats to understand sharing behavior and donation behavior because they lend themselves to the same kind of social dynamics. They are highly social animals. They live and feed in groups. They have unique sharing behavior that has resulted from the fact that vampire bats not feeding for around 70 hours will perish because of starvation. So they're very sensitive in that way. So when bats in the same group, same roosting group, go out and feed at night and come back, those animals that did not feed for that night will have food donated to them from other bats in the form of regurgitation. Clark and Wilkinson shows in their 2013 study that associations between animals can be formed by previous food sharing, grooming, and genetic relationship. Similar to in people, this study found that the sex of the donor is very significant. And these are the relative importance of those factors found in that study. Carter and Wilkinson followed up on that study, showing that as risk increases, the amount of nepotism or the relatedness factor increases. And these studies are potentially powerful models for understanding cognitive enforcement of cooperation because this behavior is completely natural, energetically costly, occurs between kin and non-kin, and can be induced experimentally. So these factors share a lot in common with blood donation. And these graphs reinforce the idea and show the data related to increases in kin selection and nepotism. And this relates to our data in that younger people may not see the reciprocity that older segments of the population see from sharing blood because they are less likely to need blood donations. And with economic downturns, higher risk in cooperation and sharing behavior may cause younger people to seek blood donations from family members. And here we see the dynamics and the frequencies of blood donations. The one-time donations versus repeat donations, forming more of a logistic distribution. So we plugged that data in. Kay's nearest neighbor was thought to be a good platform to predict. There were some good things out of it. The sensitivity was high, the precision was high. However, with the test data, the error score was rather high. So we used, because of this small data set, we used best subset BIC selection, where we significantly lowered the test error score, and we did CP, Mallow CP selection on that same data set, came up with the full 4 metrics that you have here, which is the intercept, months since last donation, number of donations, total time donating, and total donations times the total volume. The best scoring model was a general linear model that included all 4 factors, and we put this model forward as the best predictor of when people will donate blood. Drawing on that, we did select from all best general linear models and came up with a slightly smaller model that didn't include total time donating. With the conclusions of this study, we find that the Python code resembling Kay's nearest neighbor is leading on public data. A 35% probability of donation is a better indicator of future donation than 50% ceteris paribus, all other factors being held equal. The GLM model with a binomial distribution was the best model. It had the lowest error on the test data set and the lowest AIC. The time donating variable should be included as the interaction term time donating by number of donations, which was mislabeled as time donating time total volume. That factor was significant. And for future data collection, we suggest including sex of the donor and age, as well as economic conditions as an evaluation of risk.